Can you hear me?
Yeah.
Okay. Thanks for the presentation. Thank you, the committee, for organizing this conference in this beautiful place, in this very nice scientific atmosphere for discussions. And also thank you for letting me show you about this work, which we did along with Professor Pablo from Czech University. He's the leader of the group there. We're working with graphene as an analog. And this work was done also with Marcelo Chiapina, which is a condensed matter theorist in China, and Mantia Sanpelli is, I think, is postdoc now in Morelia, Mexico. And this work was published in this paper, PRD paper, and also there is a second paper in this conference of ICHP in Prague, where we discuss some other aspects. So let me say that Alfredo Iorio from now more than 10 years ago, he started this enterprise that using graphene as analogs for, let's say, fundamental systems that one way or the other cannot be tested by direct experiments or direct astrophysical observations. This work is marked on that, and I will refer to this review along with Giovanni Acquaviva and Lucas Maldoni, where they in this very fresh review, I think it was published 2 weeks ago, was discussions and reference for this enterprise, graphene enterprise, and also in the opposite sense, in the sense that inspired by graphene, trying to understand more fundamental systems, as in the talk of Lucas Maldoni we can learn in his very nice talk. So, let me introduce just roughly geometric interpretation of torsion. Suppose that you have two vectors in a general manifold, and you try to make a parallel transport between the parallel transport this vector, this key vector, along this theta, and then you parallel transport here, you have to consider the connection there. This is if you take into account the connection, and now you try to parallel transport this theta along this he, and you get this other vector. If you see that the parallelogram doesn't close, this is a signal in this infinitesimal parallelogram doesn't close, you see that you have torsion. This is, of course, if you make the computations, this difference is, of course, the difference between the connection gamma mu minus the connection in the lower indices mu, which is the definition of torsion. Of course, in GR, it is basically assumed that torsion is zero. This is one of the things that Élie Cartan asked to Einstein in the late 20s, why he assumes that torsion is zero in his theory. Einstein replies that he prefers economy in fields, but Cartan replies that he prefers economy in assumptions. So this was the controversy at that time. Of course, there was a renewal of torsion for instance, a paper by Keeble in the 60s. He showed that torsion is related to the fermions are could be a source of torsion, and there are many other models, cosmological model taking into account torsion, and also the models of more fundamental models as the Lucas Maldoni talk, for instance. So, fortunately for me, in his presentation, Alfredo was already introduced all the conventions, so I will, as I have not much time, I will go very roughly here. I will rush. I will just remember you that if you consider only time-bending approximation, only next to near neighbors, and expand around so around a Fermi point, you get this behavior of the pi-electron behavior as a Dirac, let's say as a fermion in as fermion as pseudo-fermion, let's say pseudo-spinor, massless pseudo-spinor. Okay, so and you get this nice cone, which is a Dirac cone, where the Fermi velocity, you have Fermi velocity instead of speed of light. You can, I refer to this classical reviews, Castro-Neto and Francisco Guinea. So this is works well for pristine material. What happens if you have, for instance, topological defects? We introduce a few topological defects. There are many topological defects. Suppose for this defect I will introduce, which is called disclination. Suppose you have the graphene, you cut this wedge, you remove it, and then you glue it. You get something like this now, which is a pentagon surrounded by hexagons of the honeycomb. And if you can embed this in a 3D, you can see something like a cone. You can do it with a piece of paper, you cut it, remove this wedge, and you glue it, and you get something like a cone. Actually, these are called nanocones, has its own electric properties. There are people researching the properties of these kind of materials. And what is nice is that if you introduce these pentagons in particular places, you get something like this, which is a fullerene. And you can see now that if you somehow zoom out, you get from these disclinations something like with constant curvature, positive curvature in this case, which reminds you to this tensile balloon, which actually did in that balloon, if you recognize this black patch are the pentagons and the white ones are the hexagons. You have actually 12 of them to make this balloon. Instead of cutting, remove, and gluing, you can cut, add some wedge, and glue it, and you get something like this. This is a disclination with an opposite sign in a convention, because you have a let's say angular excess instead of angular defect. You get a pentagon, heptagon, surrounded by hexagons. And if you distribute this in different places, also I think there are more subtleties because you have to also add some pentagons. You get this kind of pseudosphere. This is a pseudosphere. It's a surface with negative curvature, negative constant curvature, and you can see this in this paper by Alfredo Guerrero and Gaetano Lambiase. And they use this as try to pointing out the Unruh-Hawking effects through the Hilbert horizon. I will refer to this paper. I introduced these disclinations to introduce now the dislocation, the other effect we are interested with. If you put two dislocations of opposite sign, two disclinations of opposite sign, one pentagon and one heptagon close each other, it's like in the process of gluing and cutting and gluing, it's like if you cut some, you cut in the lower half plane, and you add some strip of width b, which is the barrier vector, called barrier vector, and characterize this effect, and then you glue it. This is the disclination. You can have many different disclinations. This, by the way, are courtesy this picture of Alfredo. He's very good making these plots, making these precise figures. So you can have, for instance, that the barrier vector is perpendicular to L, which is the x of the dislocation. This is for the case for the H dislocation I showed you before. Discrete dislocation is when the barrier vector is parallel to L. But in both cases, I would like to show you that you need to circuitize around the axis of dislocation. When you circuitize and you realize that the path or the length of the path is different from the case of pristine graphene, for instance, you realize that you have this barrier vector and you have a dislocation. Then, as well as I show you, I'll try to convince you that when you use disclination in the graphene from the lattice point of view and you zoom out, you get something with positive or negative curvature. So disclination are related to curvature. Also, it's true that dislocations are related to torsion. Through this relation, and we refer, you can find this in the classical Kleiner book, Gauge fields in condensed matter, the volume 2. This is somehow saying that torsion is the surface density of barrier vector. So, what happened now if we try to make the starting with an action? Let's go now to the theoretical part. We started with an action in which has in a space-time which have torsion, and you minimal coupled with torsion in the sense that you consider the same fermion field as in GR, but instead of a general manifold, you consider that instead a manifold without torsion, you consider that you allow that they have torsion, and then you can play with you can make a computation and skip it all the computation, and you get something like this, which is this part is the GR part, in the sense not GR, it is fermions in a curved space where this D is the covariant derivative. Consider only the Levi-Civita connection, the standard one, and you split with the torsion part, which you can see here, epsilon is the Levi-Civita tensor. You can see that the fermions are coupled with a totally antisymmetric part of torsion. As torsion has 3 index, you can see that this is only possible to have a non-zero here if you have at least 3 dimensions. This is why these people, led by Maria Basmiliano in Madrid, they also at the beginning tried to use graphene to spot some torsion there. And the conclusion with these novel results is that in graphene, because we have 2 dimensions in graphene, we cannot spot torsion because this is 0. We don't have enough dimensions. But our proposal here to circumvent this problem, to overcome somehow this novel result, is to what if we allow to time play the role of this 3rd dimension. In our approach, because we started with an action, we have a 2+1 dimension, so we have 3 dimensions here. In such a case, we perhaps has the chance that this torsion will survive. The total antisymmetric part of torsion will survive somehow. So, let me now introduce these exotic time loops in this Gendarker experiment, let's say. Suppose that now in pristine graphene, you have these black dots, which are particles. This is again a very nice figure from Alfredo Iorio. Suppose that the particles goes in the y direction, this black dot goes until y star and come back, and then the whole limit by this particle. You can try to do that. You can try to move this fermion, this electron, through a semi-electric field. Sorry. Then the whole will do the opposite path until minus y star. And then if you go to the yt plane, you can do that y in this case is horizontal and t is vertical. It's like you allow that the particle go until, thank you, go until y star and come back to 0. At the time, let's say 2t star, sorry. And the black and the white, the yellow points, which are the yellow points which are the hole, is like go until minus y star and come back. So taking the point of view, in this case, the holes are like antiparticles, and taking the point of view, sharing the point of view of Feynman that, let's say, the antiparticles are particles going back in time. It's like as the whole is like going back in time, it's like we have a particle, as the whole is the particle going back in time, sorry. It's like we have a particle going until 2t star, and from 2t star going to 0, 0, making this exotic time loop in the yt plane. This is for the pristine graphene. What happened now, our proposal to spot some torsion is what happened if we introduce a dislocation here. Suppose that in the lower half plane we introduce a dislocation, characterized by this barrier vector, and then you see through a magnetic field plus an electric field to allow to the particle moves. Suppose that in this xy now plane you allow that the particle goes in this circle through this upper half plane, and you allow that the hole, which are for us the antiparticle, goes in the lower half plane, and it's the hole will find some obstruction, cannot go directly as the half upper plane particle, and then you cannot close this loop somehow, and this is perhaps spotting to some torsion. So let me show you the future works. I show you just half of the paper, let's say. I will show how to translate this to a measurable quantity. We move some steps there in the rest of the paper to go there, to ask to the experimentalists how to measure to see this effect, which is just with an experiment. Also important is to know what is exactly the relation between barrier vector and torsion. I show you this formula, this general formula, but in the practice it's very difficult to spot if that is some particular disclination goes to one particular torsion or one to main, or main to one, etc. And of course, these two things must be solved in order to reach our main goal, which is making a real experiment in a real lab, this kind of experiment. So thank you very much.
Questions? It's one over there.
Thank you for your talk. I have two quick questions. First of all, what is the intuition for using graphene as a model for space-time, if you can explain that quickly? And the other thing is light does not couple to torsion. So how would you experimentally show that with graphene? What would take the place of light?
Thanks for the question. Good question. The first question was
what is the fundamental intuition to use graphene as a model for space-time? That doesn't seem obvious.
Let's say somehow I skip the part when you can show that the pi electrons can be seen as a fermion in a 2+1 in, let's say, space-time, and then you can try to, for instance, let me say if I understand your question. So, for instance, if you have these dislocations or disclinations, you can have a curved space-time and try to test fermions in curved space-time. This is one of the spots.
Oh, okay, because it's easy to manipulate. Is that the reason?
It's not so easy to manipulate as we want to be.
But why,
but
why graphene and not something else?
Because in the case of graphene, you can spot a massless fermion, you have guaranteed.
Okay.
In other case, there are other Dirac materials. You can use another, like Shermanian, for instance.
There's a whole family.
I'm familiar
I think
materials.
it's the low energy excitation is like a Dirac, similar to stick. So that's the thing. Okay. All the materials don't have that.
If you have a zero in the Fermi surface of the material, then near the Fermi surface is relativistic. The Fermi.
That's the point. Yeah,
That's,
all the materials
those materials will have zeros.
P squared.
That's right.
Sort of.
So, and the second question was.
How light does not couple to torsion, okay? And I'm sure Einstein and Dirac did not know that at that time. But how would you show that an analog of that with graphene? Would you try to put phonons through it and see that doesn't?
I didn't mention, but in this case, we doesn't take into account that the topological effect has dynamics. Let's say they are fixed. We are taking just trying to spotting this coupling between psi and the torsion. This is a minimal model including torsion. There could be lot of models. We need the experiment to try first to calibrate it,
Okay.
and then to start to test theories, let's say, properly.
We have another question.
Well, it's a very interesting talk. Thank you.
Thank you.
As you know, in the Poincare gauge theories of gravity, a source for torsion naturally is spin. But spin being a quantum feature exclusively, it could be that torsion also is a purely quantum feature, not there in classical theories, unlike gravity. And then what do we have in quantum theories? We have just gauge fields, the standard model. So there are actually some ideas to interchange the Yang-Mills coupling constant with spin as a source for gauge fields. So just as you are doing analog gravity models, can you do analog gauge field spin models? That would be very interesting because torsion is that in that gauge fields are torsion, so to say.
Yes, I never see that. I don't know if you, but it's an
All gauge fields here are geometric. So, for instance, if you deform the structure, then you have a sort of a U-plot.
The thing is, it's all emergent. So matter and gauge fields.
Yeah.
So the simplest thing to do is to do nothing. And you have the Dirac objects, and they look like pseudo-relativistic Dirac fields in flat space. And that's why people are interested. Then you can squeeze or deform the material without introducing defects, and this results in an effective U1 or maybe go as sort of non-abelian type of gauge fields. Then you can start adding defects of a disclination kind, and you have curvature. And that's the way. So
I was
everything goes
asking
step by
for a
step.
slightly different viewpoint. Mass energy goes with gravity. Spin goes with torsion/gauge fields. So in this experiment, can you somehow, do analog model of spin and gauge fields?
Excuse me, maybe
Later,
discussion.
sorry.
It's a deep discussion.
However,
If I can say just one word, no, in the center here, all this stuff is sort of background. We don't know what Pablo was saying, we don't know about the dynamics of that. To address your question, you have to have dynamics. Spin being the source and matter the mass.
Okay.
thank you again, and